Hi students, how exciting, a new inquiry, a new unit, a new chapter. So 5.1, and the big question we're going to consider is, why is anti-differentiation a better name than integration? Before we look at these little questions a little bit more, there are two things that I'd like you to do just to inform your thinking. First is the Desmos matching activity, which you should have seen on Classroom. The main bit I'm interested here is this bit in the middle where we have to take the red function and then try and find the antiderivative. And as you're doing that and you're thinking about, okay, antiderivative, it's like the inverse of the differentiation. As you're trying to pair them up, what I'd like you to do is think about like the mental process that you have to go through whilst you're doing that. And I don't want to say too much more about it at this point. And then the second thing I want you to do is then watch this video, which again is on Google Classroom, which talks a little bit about the idea of integration and this idea, the fundamental theorem of calculus. It's a really good video. It takes a little bit of time, but honestly, it will give you an excellent grounding as we go into this topic. So, I'm going to move on. I'm going to assume that you've done both those things. And here we are. Is differentiation a one-to-one process? What does that mean for integration and anti-differentiation? What are they one-to-one processes? And then informed by that video, what's the difference between anti-differentiation and integration? We're going to go on to the notes, but before we do that, I want you to have in your head an idea of the answers to these questions, and we'll address them as we go through the notes. What we're going to do today, really, is just try and get our heads into this, the idea of anti-differentiation, and really the thought process. So, we've got our first page. Have a scan of it and see if you can think about what's going to go in these gaps and in these boxes, and then I'll talk you through it bit by bit. So, anti-differentiation, the clue is in the name here. The definition of anti-differentiation is that's the inverse process of differentiation, and it always involves thinking backwards. And when you did that Desmos activity just now, what I hope you realized as you were doing it, if I would just take a look at it, is whilst you're trying to do the matching and move from the red to the blue, what you actually have to do is kind of reverse it and start with the blue and then go to the red. So in order to find the antiderivative of one of these, what I actually need to do is start with the function or the answer, and then think, well, what is the derivative of this? So for example, this straight line is one of the easier ones. If this is the answer, well, the derivative of this, the gradient is constant, so it must be a constant function. So we pick this red one here to go with it, and then we check our answer and we think, okay, well, if this is the function, well, the antiderivative of that must be this. If that's true, then the derivative of the blue must be the red. And we think, yeah, it's a constant value and it's positive, and so it must be this one here. When I talk about thinking backwards, that's exactly what we're talking about, and it doesn't matter whether what we're looking at is graphs or what we're looking at is algebra. Anti-differentiation always involves kind of thinking through the differentiation. So to look at these boxes here, if my question is, what is the antiderivative of 8t? The only way for me to answer that is to think, well, what do I know that gives me a derivative that's similar to 8t? And because this is t, well, we know that something that gives me a derivative of a multiple of t is t squared. But actually, if I differentiate that, the 2 comes in front, so it gives me 2t, which is close but not quite right. So instead, I need to multiply this by 4. If I differentiate 4t squared, that gives me 8t, so I'm happy and it's correct. Over here, in order to anti-differentiate minus t squared, what I need to do is what I need to think is, what do I know gives me a derivative that's close to minus t squared? And because it's t squared, I think t cubed. And then I think, but if I differentiate t cubed, that actually gives me 3t squared, which is not quite right. So I need to divide it by 3, and I need to put a minus sign in. Let me check that. If I differentiate this now, I multiply by 3, which cancels with the third, and I reduce the power by 1, so I get minus t squared, which is all good. And then if we're going to build it up a little bit, and we get this expression here, t times 8 minus t, and we think, okay, what's the antiderivative of that? Well, what we've got to do is split it into parts, and then we realise we have the 8t and the minus t squared. We deal with them separately, and we realise that an antiderivative must be 4t squared minus a third t cubed, using the first 2 parts. And that mental process, that thinking backwards, is just going to be so key to pretty much everything we do in this anti-differentiation unit. So, now in terms of answers to the questions on the first slide, well, differentiation is many to one, right? Because lots of different functions can have the same derivative of dy by dx. The derivative of this one, well, that's 12x, and I can come up with other functions that have a derivative of 12x just by adding constants. And as long as I keep the 6x squared plus 3x the same, I can add or subtract whatever I want, either plus 7 or minus 12 or anything else, and it's still going to have that same derivative. So differentiation is many to one, meaning anti-differentiation has to be one to many. So y equals 2x, well, that's got a derivative of y equals x squared, because, sorry, an antiderivative of y equals x squared, because y equals x squared differentiates to 2x, but also y equals x squared plus 17, and y equals x squared minus 324. All of those have derivatives y equals 2x, so anti-differentiation is one to many. And all these functions, what you notice is they're all vertical translations of one another. And in fact, we can see that represented on this diagram here. All of these are part of the family of solutions. And that's what we would call this, the family of solutions. And so if we start with an original function f of x, we use our normal little f. We call the antiderivative big F of x, and there's always going to be a plus c, and the plus c could be anything. So big F of x is the antiderivative of little f of x, or in other words, the derivative of big F of x is little f of x. And we could write that more formally by saying if f dash of x equals little f of x, then the antiderivative, or the integral, this is a different type of notation, of f of x, little f of x, is big F of x plus c, where c is just a real number. And this notation, I know we've seen before, but this has been around since the very origins of calculus, and it goes back to that dispute between Newton and Leibniz that we heard about. But this idea of an integral, it means the reverse of differentiation. So on the second page here we've got a table, and what I'd like you to do is have a go at doing the thinking backwards that's going to help you fill out what's on the page here. Think about the kind of things which you know differentiate to give you something like this, and then adapt them to fill the table, and then we'll worry about the conditions on those things in a second. So pause the video, have a go, then we'll go through it. Okay, so you've tried this question. If I'm thinking of something which differentiates to x to the power n, well, I know it must be like x to the power n plus 1, but if I differentiate x to the power n plus 1, it's going to give me a times by n plus 1 in front, so I need to divide by that. And so the general form of my solution here is going to be 1 over n plus 1 times x to the power n plus 1, but we have to remember we must have a plus c, because anti-differentiation is a one-to-many function. There could always be this constant term, that could be anything. In terms of the condition on this, well, this works for nearly all powers n. The only one it doesn't work for is n equals minus 1, and we're going to come to that separately in a second. Generalizing this, for the second one, well, we're still going to have this idea of to the power of n plus 1, but now, if I were to differentiate this, not only would I multiply by n plus 1, but I would also multiply by the a from the chain rule. So now, as well as dividing by n plus 1, which I still need to do, I also need to divide by a. Now I've fixed it so that the derivative of what I've just written is what was in the box, and so this must be my general form of the antiderivative. What differentiates to x to the power minus 1? Well, it's this special case of log e of mod x, as we covered in the last chapter, and this, putting in my plus c, only works for x not equal to 0, because that's when the mod x is not defined. Also missed a condition up here, so here we must still have n not being equal to minus 1, because to fill this in, we kind of combine both the things we've done so far. We're going to have log base e of mod ax plus b, but if I were to differentiate that, I'd also multiply by a, so I need to divide by a, plus c, and in this example, the thing that we're finding the log of, so ax plus b, cannot be equal to 0. What differentiates to give me e to the power ax plus b? Well, very close to e to the ax plus b, but there must be a 1 over a in front to cancel with the a when I bring it down. So there we go. What differentiates to give me sine? Well, cos differentiates to give minus sine, so it must be minus cos. And then starting to get the idea with this ax now, I must have a 1 over a. My check, if I differentiate this, I multiply by a, the cos goes to minus sine, the two minuses cancel, so I would get sine ax plus b. I'm happy. And then this one, what differentiates to give cos? What sine does? I must have a 1 over a because of the chain rule and the a inside the bracket, meaning that overall I've got 1 over a sine ax plus b plus c. Notice, I hope you noticed as I was talking them through, I was kind of mentally checking every single one with differentiation, and that's part of this process. You know, you come up with something that you think differentiates to something close, and then you adapt it, and then you check it in your head. Let's talk quickly about notation in this first lesson. If we're talking about definite integrals, I think this is what you guys have not done before, and this is where the fundamental theorem of calculus really comes in, and we're going to come back to this later on in the unit, but we're just going to touch on the notation now. The definite integral is defined as the area under a curve between 2 points, a and b here. So if this is my function f of x, the area a is the definite integral, and that's between two limits, a and b. We call it a signed area because it's positive if it's above the axis and it's negative if we're below. We'll come back to that again later. And this idea in that video that you watched, the fundamental theorem of calculus, and this is pretty radical, is that this definite integral can be found just by looking at the antiderivatives at the endpoints and subtracting them. And that's a pretty random idea, and in fact it's not obvious. And those two definitions, the area under the curve and the inverse process of the derivative, we've come at those from completely different angles, and yet they give us the same result. They're related. And when we come back to talk about the fundamental theorem of calculus, we'll talk about exactly how and why we can connect them. Just a little technical note, in this expression, the thing that's inside this integral, we have a name for that, and that's called the integrand. So that if you hear me in the videos talking about integrands, what does that mean? Well, that means the thing that you're integrating. It's just technical bit of vocabulary. So, it's going to be a short one today, just a couple of examples to look at. First thing I want you to do is just try and put this into practice. Can you integrate or anti-differentiate these three functions? Pause the video, have a go. Okay, so you've had a go at this. If these are all little f, then the antiderivative is given by big F of x, and I'm looking for something which differentiates to give me sine. Well, minus cos will differentiate to give me sine. I'm going to keep the argument or the angle the same, and then what I'm going to think is if I do differentiate this, there's also going to be multiplied by 3 because of the chain rule, so I need to divide by 3. So my answer is minus a third cos of 3x minus pi by 4, but I need to remember, always need to remember, my plus c. Second one, well, what differentiates to give me e to the power 3x plus 4? It's going to be something like e to the power 3x plus 4, except if I do differentiate this, I also going to have to multiply by 3, so I must divide by 3 to cancel out. Checking this, if I do differentiate it, the exponential differentiates to itself, but I multiply by 3, the 3 cancels with the third, leaving only the coefficient of 1, and I must remember my plus c. And part c here, what differentiates to give me 6x squared? Well, it's going to be something x cubed. X cubed differentiates to give me 3x squared, so I need to double it. 2x cubed works. Looking at the next term, what differentiates to give me minus 2 over x squared? Well, that over x squared is x to the power minus 2, so I need to up the power by 1, so it's going to be something like 1 over x. If I differentiate this, I'm going to multiply by the minus. That's going to give me the minus sign, that's okay, but it's not going to give me the 2. So I'm going to have to add in a coefficient of 2. I think it's going to be 2 over x. I check that. 2 times x to the power minus 1. If I differentiate it, I multiply by minus 1, and I reduce the power by 1 to get minus 2. That looks correct, and so I'm going to add the c and call it a job done. So that's our process. Those are very simple examples. And you can see how critical it is to really have your differentiation down when you're doing this. If you do want to go back and do more practice on the differentiation, because you're just realizing you're not that fluent, you need to spend some more time memorizing the rules, getting it all in your head, then I would definitely recommend that. It's super important. I know we've talked about memorization before, but it's super important that this stuff comes to you very quickly and naturally when you're trying to do this like flexible backwards thinking for anti-differentiation. Speaking of which, you're going to need that for these 3 questions. These are definite antiderivatives, definite integrals. We looked at the formula just briefly before, So I'd like you to try these questions, pause the video, and then we'll go through them together. Okay, so you've had a go at this. What I'm going to do is introduce just a little bit of notation. If I'm trying to find an integral like this and it's not been defined, I'm just going to call it I. Capital I stands for the integral. And when I'm doing this, in the process of integrating, I'm going to find the antiderivative first, and then I'm going to substitute in these limits. And in that process, I move to square brackets. So I'm going to anti-differentiate sec squared of 2x, but before I substitute in the limits, I'm going to write down my answer. So after we have a definite integral, our next line is going to be square brackets with the limits maintained and still written on the right hand side, just like this. So you'll get into the habit of this. We're going to do it every single integration question we do when it's a antiderivative. Sorry, when it's a definite integral. And yeah, you'll get the idea. So what differentiates to give me sec squared? Well, I know that one. It's something like tan. So it's going to be something like tan of 2x. But if I do differentiate tan of 2x, that's going to give me 2 sec squared of 2x. So I've also got to put a half in. That's my expression. Now I need to evaluate it at the two limits, and I always do the top one take away the bottom one. So the top one is going to be a half tan of pi over 4, because 2 times pi over 8 is pi over 4, and then I'm going to subtract a half tan of 0. Knowing my tan values, tan of pi over 4 is 1, tan of 0 is 0, so this is going to just be 1/2. For part B, I'm going to use this idea of I again, and my square brackets, and my limits. And now I'm thinking, well, what differentiates to give me this? Well, it's an expression like ax plus b to the power 1/2. So I know I'm looking, I wrote the a there, at 2x plus 1 to the power 3 over 2, because the power always jumps up by 1, right? Then I need to match my coefficients. So we can do a little bit of scrap working out with this if it's helpful, but if I differentiate this, I'm going to multiply by 3 over 2, and I'm going to multiply by 2. So overall, that's going to give me multiplied by 3, because the 2 is going to cancel with the over 2. So in order to make it balance, I need to put a 1/3 in front. Now if I differentiate this, the 3 cancels with the 3, the 2 cancels with the 2, and I just end up with 2x plus 1 to the power 1/2. Notice that backwards thinking, that flexible thinking. Now if I substitute in, I'm going to get 1/3 times 3 to the power 3 over 2 minus 1/3 times 1 to the power 3 over 2. If I simplify this, the 3 is like 3 to the power 3 over 2 divided by 3 to the power 1. That's going to give me just 3 to the power 1/2, or root 3. The second term just gives me minus 1/3. So a nice clean answer is root 3 minus 1/3. Then for part C, the capital I for the integral, square bracket for when I've done my anti-differentiation. What differentiates to give me something like 1 over 4x plus 2? Well, I know it must be something like log e of mod 4x plus 2. But if I do differentiate this, I get this 4 in there that I don't want. So I've got to put the quarter in. Quarter cancels with the 4. This gives me what I'm looking for. So now I do my substitution. I'm going to have a quarter. Here I'm just going to write it slightly differently. The quarter is a common constant through both terms, so I'll factorize it. And I'm going to have log e of mod, substituting in the minus 1 is going to give me minus 2. And substituting in the minus 2 is going to give me minus 6. So starting to simplify using my log rules, this is a quarter log e of mod minus 2 over minus 6. That's the same as a third, so it's a quarter log e of, it doesn't need to be a modular sign anymore, brackets, a third, and a third is the same as 3 to the power minus 1, so this is minus a quarter log e of 3. And that's probably the nicest and cleanest solution. So hopefully you got those, and if you didn't, there's going to be lots more chance to practice in today's exercise. But the one final skill for us to look at is this idea of graphing them. And we could kind of think back to that matching exercise we did on Desmos right at the beginning. We still, when we do this, have to do this like thinking backwards. So I've got this graph on the left-hand side, and I'm thinking, well, what kind of thing, I realise I drew this pretty badly, what kind of thing is this the gradient of? So this is, if I look at this function, it's always positive, meaning I must have a graph that always has positive gradient. I'm just doing facts here. Always has positive gradient. This is a quadratic, so what I'm going to be looking for is going to be something like a cubic, because a cubic differentiates to a quadratic, so it's going to be a cubic shape. I can see that the minimum gradient is 2, so the minimum gradient is 2, and that occurs when x equals minus 1. So if I now try and draw this, the point that I've got is minus 1, and at that point the gradient is going to be the smallest it gets, so that's going to be like a point of inflection, and that's going to be a gradient of 2, so it's positive. And then on both sides of that, the gradient is going to increase, and it's going to give me this kind of cubic shape. And then that description so far would give me a whole family of curves, because they could be anywhere on here. We don't have, sort myself out, apologies. We don't have any sense of where it's going to be, because all we've got is just information about gradients, except that in the question they tell us this: f of 0 equals 0, big F of 0, which means we must go through this point here, 0, 0. So as I sketch it, I'm looking for a cubic shape, I'm looking for a point of inflection that is kind of level with this minus 1, that gives me a minimum gradient, and then I'm looking for an increasing and positive gradient after this point. So this sketch here is the best that I can do with the information I've got. This is a point of inflection with gradient 2. So that backwards thinking again coming into play to help us sketch the graph of the antiderivative. So that's us for today. I want you to be really conscious of this backwards thinking process as you go through the exercises. And this is the scheme of lessons that we're going to do. We've got 10 lessons to get through, and after we've done all those, we're going to get on to the next tests. So best of luck with it, and as always, let me know if you struggle with any questions. I'll do my best to get you some support and some feedback with those. Speak soon.